Okay. Well, I will share my screen then. If you haven't seen the PDF that I'm talking about, I emailed it out maybe 10, 15 minutes ago. So go take a look at that. And we'll just kind of go through it at whatever seems like a reasonable pace. And I'll do some annotations on it so I can, actually, I won't be able to send it out, but the recording will be good. All right, can we see this?
Yep.
All right, for number one, is it given on basically given the description that I am giving you for this here? What's the right selection to make from these brackets? So generally speaking, when X is close to 3, what's Y doing? Increasing, decreasing, or staying the same?
I got decreasing.
Okay, I got to vote for decreasing. Anybody else want to agree or dissent?
I agree.
Okay, I think that makes sense to me. So yeah, we know basically that. Is there a way to represent this sentence much more concisely?
I said, basically dy over dx equals -8 at x at sine x equals 3, and you could also translate that to dy equals -8 dx. So what that means is that because the rate of change of the slope is negative, the value is decreasing.
There you go. Yep, and all those things are true. But yeah, I mean, actually that's already given. I didn't see this up here, but yeah, dy dx equals -8. All right, so for the next set of brackets here, is it, so we already said decreasing. Is that happening slowly, moderately, quickly? What's the right
That's
adverb to
kind of
throw at this one?
Judgment call, depending on context, because I can think of contexts where a slope of 8 is pretty radical, but others where it's pretty moderate. So,
Yeah.
Yeah, I need some context as well, because that sounds a little bit too vague.
Yeah, this one's weird. I'm gonna go ahead and force my opinion on you all as quickly, just because based on me having taught this class before and seeing some materials that maybe you don't have access to, you know, this is approximately equal to 1 or plus or minus 1. This would be, you know, something between, I'll just call it R. So if you got something like a 1/4, I would call that slowly. And quickly, I mean, that's a pretty steep slope, especially when you're comparing it to plus or minus 1.
Yeah, that's the context that I was thinking, but I just want to make sure.
Yeah, and like I mean,
presumably it's not exactly 1, like, yeah, and it's a judgment call, like 0.8 to 1.2 is probably going to be moderate.
right, and that's why this question I think is a little. I mean, it's imprecise for sure. But you know, the really important thing we know is that in this vicinity, the slope we have is -8. Any questions on that before I clear my screen and scroll through?
Clear away.
All right. Let's do this for these next 3. I'm going to give you all a few minutes to think about these and write some stuff down. Yeah, in the meantime, I will remain quiet unless anybody has any questions, but you know, staying in one group, big group right now, I feel like breakout rooms make it, I don't think there's as much collaboration going on there as I would like. And I think just not being in person just makes that really hard to make that happen. So just because I'm having you all work on your own for a bit, don't think that I'm asking for silence. If you have questions or if you have thoughts about anything, please say something or put it in the chat. This works a lot better if we're bouncing ideas off of one another. Do me a favor, everyone. When you're done with 2, 3, and 4, send me a private message in chat that you're ready to move on. And just because I've never thought about it, can you all see that I have the chat window open right now?
No, I can't.
Okay. All right, good. All right, I haven't heard from everyone, but I've heard from quite a few of you. So let's talk over 2, 3, and 4. So at the moment, t equals 5. I'm giving you dx dt equals 3. So what does that mean? So decipher that in English. I
Okay,
guess.
so I put given small change in t near t equals 5, the rate of change of time is 3 times that of the rate of change of the particle. And I basically in formula, I said dx equals 3 dt.
So I'll put that over to the side here. Dx equals 3 dt.
Yeah.
Can someone else give me what their description of this this situation is?
I put for any change in t near 5 seconds, the particle is moving at a rate of 3 centimeters a second in the x direction.
Okay.
I like
I think
that.
both of those you have a lot of commonalities. Both of those are pretty good. Anybody else want to throw something out? So I'll try to recreate from what I heard. So at t equals 5, I guess, or near it. And I'm pretty sure both Mark and Michael said this correctly, but I really feel like it needs to be emphasized again. So when I say the rate of change, how specifically should I try to phrase the rate of change of what?
X with respect to t.
Yeah, of x with respect to t. Is 3, and then I want units. So what should they be?
Centimeters per second.
Yeah, centimeters per second. So one thing and the reason I asked for an extra piece of specificity around the rate of change, you know, it's one thing if you're only dealing with 2 quantities like we have done for most of this semester, and really probably most of your math careers. But now we're bringing in this third quantity, this parameter. So when you're talking about rate of change, you really can only unite 2 quantities that way. So it really is important to specify which those are. But I think this is great for this one. Similarly, we can say something about dy dt.
I would, the simple version would be to just substitute y for x and negative, and however you want to write the rate, but now it's -3/4 instead of +3.
Yeah. And in fact, let's be a little more descriptive about this. We said the rate of change of x with respect to t. What does x represent?
The either, depending on how you want to label the axes, either the horizontal or vertical displacement.
Yeah, so we'll stick with convention. Yeah, we'll call x horizontal and y vertical. So t equals 5. Really shouldn't say at t equals 5 because really it's in some neighborhood of that time. The particle is moving which way?
Down. Right? Down?
Yeah, absolutely. Yeah, I did negative. So yeah, we'll just go with convention. So positive y is up, negative y is down. So moving down at a rate of -3/4.
But if it's going down, isn't it a positive rate?
Yep, you're absolutely right.
I thought it's just -3 because 4 is dt.
So let me answer that with this. If I write a over b equals 2/5, does that mean that a equals 2 and b equals 5?
I do not know.
I don't think so.
So yeah, we can't say that for sure. All I know is that a like, for example, what if I
410.
did A equals 20, B equals 50?
And then you just simplified it to,
Yeah, but yeah, that ratio, it certainly holds, but I can't say for sure that, when you say a fraction is equal to some other fraction like here, that does not mean you are saying the numerators are equal and the denominators are equal. You're just saying something about the ratios there. So I'm going to actually go back to the way that Mark phrased this with the other one was, I can kind of rearrange this to say dy equals negative 3/4 dt. And if we go back to, those, what were the three adverbs that were on there? Slowly, moderately, and quickly. I think this one would certainly not fall under the description of quickly.
Moderately slow.
Yeah, it's going downward moderately. It's a little closer to 1. Certainly closer than 8 is for sure. The other thing I want to bring up is, are we okay with me basically taking away this negative sign the way I've worded it?
I'm a little confused on what you mean by the particles moving down.
So I know that dy dt is negative, and we're kind of saying this. I mean, we're just going to go with what our kind of instincts tell us. X is horizontal, y is vertical, positive is either right or up, and negative is either left or down.
So
So
for number 2, we should be saying that it's moving 3 centimeters per second to the right, shouldn't we?
yeah, and that's why I was saying I just worded 2 and 3 differently. I think 2 is a little more, mathematically stated, and 3 is a little more, plain English. But they're both totally good descriptions. I didn't want to totally mimic what I did for 2, just to give it a different look.
Right.
Back to this question though. So are you okay, Kevin, with the fact that the particle is moving down at this moment?
Is it because of this rate?
Yeah, this rate. What specifically about this rate?
Is it because it's negative?
Yep. So yeah, the rate of change of y, which is basically the vertical position of this particle, the rate of change at this moment is negative, so it's downward.
Okay.
And number 2 says that basically at this moment, the particle is also moving right.
Right. Because
right.
it's 3.
Yep. Well, because it's not specifically that it's 3, but because it's what?
Positive?
Positive. Yeah, exactly.
Okay. Okay.
All right. And then 4, find the value of dy dx of t equals 5. So how do I find that?
Just negative 1/4, right?
Negative 1/4. How'd you do that?
We've got dy and we've got dx. So dy is negative 3/4 and dx is 3. So divide the one by the other.
Right. And this is
-3/4.
something that, finding, when we first were talking about parametric functions, we talked about, how you can eliminate the parameter. Basically, how do I unite these things just in X and Y without involving T? We're doing the same kind of thing through differentiation here. So, and I'll just write this a different way to kind of show why. I don't know. I think this makes it pretty clear that this will actually yield dy dx. But dy dt was equal to negative 3/4. And
3.
3, right? So yes, I agree. That's going to be negative 1/4. And what are the units?
This is still centimeters per second, right?
Do we agree with that?
I don't think seconds belongs there.
Okay, remember, because is y expressed in seconds?
No,
Is x?
no.
So let's look at it this way. I'm going to put the units back in here because certainly
Just
this
for
is negative
clarification, but is this all like basically the same numbers we're using? It's number 4 basically the same numbers we're using, numbers 2 and 3.
Yeah, absolutely. Yeah,
Okay.
that's where these come from.
It's unit.
Just want to make sure.
Yeah, this is going to be unitless. Because let's just talk about this. What does dy dx mean?
Rate of change of y with respect to rate of change of x.
Right. And what specifically do y and x represent about this particle that we're talking about?
Position, displacement.
Right. Position. So yeah, basically what this thing says is, and I think it's still really useful to look at things like this, dy equals -1/4 dx. But for every change in x, which is going to be a length, then y changes by -1/4 times that change. Yeah, in this case, there are no units. I mean,
Or centimeters per second per centimeters per second.
right, and I'm not sure if there are any engineering majors here, but later on in electrical engineering, sometimes you see units like volts per volt. But really, you don't even need to have units here, because the two quantities that you're comparing they're measured in the same way. All right, any questions so far on these before I clear and scroll to the next stuff?
I was just gonna say 4 reminds me of like a physics class.
Yeah, a lot of applications there for mechanics.
Is there a way to tell which direction it's going, like horizontally, just by looking at dy over dx?
Yes and no. So let's. I don't know where this thing is at t = 5, because all we know is rates of change. But let's say the particle is right here. Which way? So let's say this. Like what direction might this thing be going right now?
I think it's going right now,
Okay.
just
You think
based
it's
off
going-
because we know that from the dx over dt.
Right. So you think it's going like straight to the right?
Well,
Well,
right and down.
Right. So it could be going this direction. Something like that. Do we know that's the case?
Doesn't it depend on the direction of the graph?
Yeah, and that's kind of what I'm getting at. Do we know what the direction of the graph is? Like, for example, do I know, could either one of these things be happening, or can I say for sure that one of them is happening?
We know that x is increasing when t is increasing, and we
Right.
know that t is increasing, so therefore x has to be increasing.
Right. So this actually cannot be happening, because yeah, we know at this moment. And remember, when you're graphing a parametric function, you're graphing t in order. So if t = 5, then the graph is going to go in whatever direction is dictated when t increases. So yeah, we absolutely know that this is what's going on. The graph is moving to the right, the particle is moving to the right and downward.
And at roughly the slope that you drew, which is kind of close
Yeah.
to a 4.
Yeah, I tried to be pretty faithful to the -1/4. That's a good question though. Anything else? All right, let's keep on going.
We don't necessarily know the speed that the particle, we just know that that's the tangent to the curve, but we don't know how fast the particle is actually moving from
Well,
so far.
could we find the speed?
That's what we should have enough information, but I don't think we've
Yeah.
pulled it out yet.
So I don't think we're going to be asked for it, but basically what we know is this: I can use Pythagorean theorem basically, because I know that dx is 3 centimeters per second, and dy is, no, the absolute value is 3/4 centimeters per second. Could I find this pure speed based on the hypotenuse of that triangle there?
If you got a calculator, you can do that stuff in your head.
Yeah, absolutely. But yeah, it's not something we're asked for right now, but yeah, we could find the pure speed. All right, let's go on to 5. And then I think 6 will take us a while. So I'm just gonna isolate 5 for now. And same drill, send me a private message when you are ready to go on. All right, I've got a lot of you. All right, so I know the second derivative is, and I'm going to rewrite this because I think that's a little weird to look at. D's, I'm not sure if Mark has used this notation before, but it's pretty common to show the second derivative.
He wrote it, but didn't explain why the squareds are, the top one is on the D and the bottom one is on the F.
I'm going to hold off on that question for now. I think it's a longer conversation than it is I think valuable for what we're doing right now. But yeah, if you want to talk about it later, we can definitely do that. But yeah, there is a reason for that. All right, so we have the second derivative is -1. What does this mean about the movement of the particle at this, around this time?
Second derivative negative means that it has to be concave down.
When you say it has to be concave down, what do you mean?
The path has to be, the graph has to be concave down at that point.
Okay, so I'm going to write that off over here. Concave down. which you're absolutely right. What does this terminology mean? The concave down.
Frowny face, informally.
How about mathematically? What is concave down getting after?
It means that the rate of change is becoming more negative.
Right. So really, and what concave down means is, at this moment, the rate of change. So when I say the rate of change here, what rate of change am I talking about?
Is that dy over dx?
Yeah, dy dx. The rate of change is dy dx is, wow, decreasing. So 2, 3, and 4 told us something about the rate of change dy dx. Now this here tells us the rate of change of the rate of change. The rate of change of the first derivative. A lot of ways to say the same idea. What units do we care about here?
If dy dx is unitless, does this have to be unitless as well?
It should also be unitless. Yep. All right. Anything else about 5 before we move on to 6?
Seems to me that this, we're not given enough information to know for sure, but this would be consistent with if you toss a rock after it reaches its peak, it's already headed down and it's coming down even faster.
Okay. So what kind of shape did you just describe?
Parabola.
Yeah. So, if this, we're given a second derivative, and if that second derivative holds true constantly, then yeah, you're going to have a parabola. So number 6 here. And I think we might have glossed past this, so I'll make it clear here. X is equal to P of t, and Y is equal to Q of t. So basically I'm telling you, around t equals 5, then I know the particle is, or exactly at t equals 5, that particle's right there. So let's just catalog all the data we had. We had the dx dt equals equal to 3. We had the dy dt was equal to -3/4. And from there we got that dy dx was equal to -1/4. And we know that the second derivative d squared y over dx squared is equal to -1. So given all that information, and you were told that the second derivative is constant for values of x within 1 of our initial point here. Given all that data, we should be able to draw a graph of our curve so for the values of x that are actually valid. So let me scroll up so you can see the whole graph. Actually, that was not that big a deal. This will take a bit. So, and in doing that, I lost the point that needs to be where.
Quick question, but will we see something like this graph question on the final exam or no?
You may. So, I mean, and really the whole point of this graph is to show that you understand like all these different rates of change and how they all work together, and just keeping everything organized and to draw conclusions. So yeah, you might not see anything exactly like this on the final, but I mean, you've seen 3 of Mark's tests now, you know how conceptually deep they are. And this is all about making sure you understand parametric functions and the calculus and how all those things work together. So I'll leave you to this one. We got about 13 minutes left. I don't think this will take quite that time, but do me a favor here. When you have something you'd like to show us, annotate on my screen and draw. And when we have a few to talk about, we'll stop there.
You
Right.
want us to annotate right now?
I'm sorry, what was that?
You want us to annotate right now, or just in a little bit?
If you, you know what, let's hold off for at least a couple minutes. That way people aren't being influenced by things they can already see. I'll let you know when to annotate, but yeah, just work it out on paper or on your own for now.
Yeah, I don't know what to do, honestly.
Okay.
So P of 5 equals negative. But there's no 5.
So what does this 5 represent in P and Q?
T.
Yeah, that's a value of T, right? But this graph here, the axes of this graph are,
fx and g of x.
yeah, or y and x. So we're not graphing T on this plot, but we have all of this information that we found from the last few questions,
Right.
that should help us, and these two here, these don't require any more investigation in T. So we should be able to at least sketch this graph, maybe not exactly, but roughly, around this point.
We're sketching dy over dx equals negative 1/4, correct?
dy dx equals negative 1/4, right?
But we also know that d squared y over dx squared is -1.
Yep. And really, yeah, you need both those pieces of information to do what's being asked for here.
I'm a bit confused by the final sentence in the question.
Assume that the second derivative is constant for values of x within a radius of 1 from the point of question. Radius of 1, basically, the graph that you end up drawing is only going to be effective in this little narrow strip here. So yeah, we have information about the second derivative, but I have no idea what the value of the second derivative is outside this this strip, because I only know that the second derivative is equal to 1 on the interval -3, -1, basically within 1 of my point.
So our
Gotcha.
graph is only going to be sketched between those two lines.
Yeah, so yeah, we don't know anything about what's going on over here. So we just don't have, the only information we have is confined to x values between -3 and -1. And those of you that are kind of having trouble getting started, I would do this. That the graph you're going to draw goes to the point -2 too. You're given that. As you go to the right, do you know if your graph should go down or up? You don't have to answer me out loud, but I think that's a good question to think about to start with.
Do we have to know specifically where these rates apply at, or can we just?
Sorry, Kevin, you're trailing off a little bit. Can you try that again?
Do we have to know like specifically where these rates apply at? Because in the previous questions, it was saying like t at values of t, or
Yeah, so everything we did on 2 through 4 was for t, value of t equals 5.
okay,
And which is the same, that's the same like kind of time that we're working around here.
okay,
because P of 5 is equal to -2 and Q of 5 is equal to 2.
Okay.
All right, if anybody has annotations they want to share, go for it.
Okay, I graphed 2 possibilities.
Yeah, I've seen a lot of different attempts. That's good. And while we're doing this, let me ask this question since it's been brought up. Is this a parabola?
No,
At least
not in the range that we're given.
Okay, I got 1 vote for no.
In the range we're
I think it
given,
would be.
yeah.
Okay, I got 1 vote for yes, it is.
Make it 2.
Okay, 2 votes for yes.
I'd say within the range, yes, but outside of it, we don't know.
Yeah, so outside of it, we have no idea. Okay, so let's talk about that in a bit too. So I am going to, what color has not been used? They've all been used. All right. So my original point was here, right? It's not even the right tool. Okay, so the original point was right around here. As X goes to the right from there, which direction should my graph go? Downward, upward, horizontal?
Down and to the right.
Yeah, and it looks like a lot of you are saying down and to the right. What tells you that that's the case?
Because dy over dx is negative, so the integral is therefore decreasing.
Very good. So start, and it's a little shallow, but it's definitely going downward. Now, as I continue to the right from there, what should I see? Should I see my graph kind of curl up, stay on this constant rate, or go down even more drastically?
It should go down a little
Yeah,
more.
concave down.
And why do you know that?
The second derivative shows us the rate of change,
So yeah,
which is -1.
so not only is my function decreasing, but its rate of decrease is getting even more significant. So I think
How can
think
we
I agree.
I was going
Go
to say,
ahead,
how can we judge how fast that's going? Because it seemed to me like it should be a relatively shallow curve at that point.
Yeah,
that I
right.
tried to-
So right now I'm just sketching.
Okay.
But yeah, I mean, one thing I will send out later is last semester I did this all exactly, but it takes a little more care. Right, for right now, I just wanted to kind of go, more or less qualitatively, or not qualitatively, but roughly on what we had here. So I think this looks pretty good for as we go to the right. But like Ben said, I could be totally off on how severely, I mean, kind of like the levels, but I think, or I know we're certainly right that it starts off by decreasing and it's going to just decrease at a more rapid rate as I move to the right. Now, as I go to the left, what's going to happen initially? Down, horizontal, up.
Still up and to the left, but less
Right.
and less so.
So it just start off by going up because, that's the rate of change says. But hopefully a lot of you said, actually, I don't think all of you said this, but I should hit a peak. Why should I hit a peak and then go back down like this?
because it's decreasing.
And what's decreasing?
The rate of change is decreasing.
Right, so my second derivative here is -1, which means, and I think it's pretty clear that if I move to the right, that rate of change will be, that dy dx will become less. But the other side of that coin is, as x decreases, dy dx increases. So because of that, I'm going to have a function that increases over here to a peak.
And I was eyeballing it, just guessing that the peak was going to be somewhere on the left side of -3.
Oh, somewhere over here.
Yeah,
Okay, and that would explain why I'm seeing a few of your graphs that don't have, that are basically, even at the left end of that interval, still sloping down. So the question I asked was, is this a parabola? So let me say it this way. Actually, I'll call it f double prime, y double prime equals -1. That's a constant, right? How would I find, I eventually want to work up to y. So how would I do that? How would I get from y double prime to y?
Find the antiderivative.
Cool. What's the antiderivative of this?
Negative x, negative y. Or no?
It's actually -x.
Okay, it is x.
Yeah, so I mean, y double prime, I'm just doing shorthand for d squared y over dx squared. Really, I'm integrating with respect to x. So I have -x plus c. We'll call it c1 because I'm not going to worry about evaluating the constant right now. So how would I get to y?
-1/2 x squared. Yeah, plus a constant x and constant.
Is this a parabola?
Yeah.
Yep,
I have a
absolutely.
quick question, but how can you get from a derivative of -1/4 to a second derivative of -1?
This was given to us.
Oh, okay.
Yeah, we weren't given the right information to calculate the second derivative, but actually we may have been. But
what's
either way, we
to,
were just given this. Go ahead, Mark.
Why would you use -1 instead of -1/4 to find the original function?
So here's the thing, y prime here, so this is your first derivative.
Yeah.
I know that dy dx is equal to -1/4,
Right.
but only at a certain point.
Yeah, it's at 3.
It's at, I think it's at, it's at x equals -2.
Okay.
So I certainly could have used that to figure out what this constant was. And in fact, I'll send out solutions later that will show you that how I did that. But right now, I was just trying to do this quickly to show that, yeah, if I tell you the second derivative is constant, then yeah, you have a problem. So it's not an accident that our graph looks like that. We're actually going to start. Oh, go ahead. Someone asked a
I
question.
was going to say with the, of course, the -1/2 tells us it's facing down, and 1/2 is kind of a shallow parabola.
Yeah, right. Which tells me that you're probably right that I made my annotation a little too sharp on the right. All right, any more questions before I stop the share here? Okay, I have 12:51. Like I said, there's a quiz today. But it's going to be open for, until midnight tonight. So if you want to take it now, you can't because I haven't published it yet. But if you want to stick around, I'm going to go publish it right now. Otherwise, take it sometime before the end of the day, and I will see you in class tomorrow morning.
Thank you, Steve.
Thank you.
Thank you.
Thanks as always.
Thank you.
Hey, Steven, I just had a quick question.
Go for it, Kevin.
What does the second derivative actually tell us about the function?
So in general, a derivative always tells you the rate of change of the function that you got that derivative from. So the second derivative tells you the rate of change of the first derivative. So
Okay.
let's just start at, some basic function, some curve. That first derivative will tell you basically the rates of change of y with respect to x for any point on that function.
And that's like how fast the function is.
Yeah, basically that
changing.
tells you the slope of any tangent line you want.
Okay.
The second derivative is basically the first derivative of the first derivative. So
Okay.
basically it tells you how fast those slopes are changing.
Oh, okay.
And I had somebody explain derivatives to me at some point as sensitivity, so that if you have something that has a high sensitivity like 8, that means you only have to change the input by 1 in order to get a really big change of 8 out of it.
Mhm.
So, and
Yeah,
that-
I haven't heard the word sensitivity used for derivatives before, but I think it's a really intuitive way to look at them. Because if you have dy dx equals 10, then think about what that graph would look like where that derivative was taken. You move a little bit to the right, you're going to move up pretty drastically.
Think about gears on a bike, that if you're in a really high gear, you move your feet just a little bit and the wheel spins a really long ways.
There's a really good animation. I'll try to find it and send it out to you all. That actually shows derivatives as gearing ratios.
Oh, I
But
like that.
I'll try to find the animation. It's not a video. It's interactive, but I'll try to find it because I think it shows a lot of cool things.
I love
Is
that.
that true?
Thank you.
Sorry, Ben. Is that true for higher level derivatives too? If you keep going?
Yeah. So yeah, what I said about derivatives is, the fifth derivative is the rate of change of the fourth derivative with respect to whatever the variable is. And you've kind of seen that with, we've done in terms of mechanics and physics, we did position, velocity, acceleration. If any of you are going into, mechanical engineering or something related, you'll see there's a third derivative, which is called jerk, which is basically how fast acceleration changes over time. But
Interesting.
really what any derivative tells you is the rate of change of the parent function. It doesn't matter if that parent function was the derivative of something else.
Right.
You can, if you have a function that you can take derivatives of 20 times, then basically any derivative tells you the rate of change of the thing above it.
Right. Okay. That makes sense. Thank you.
No problem.
I just say because I might need help with the